Okay, so we've seen that the projection of the r double prime of t vector perpendicular to r prime of t has a magnitude that's equal to the magnitude of the cross product of these two vectors divided by the magnitude of this vector. Now, remember that the curvature is the derivative of the unit tangent vector with respect to x. The unit tangent vector is obtained from the r prime vector by simply dividing it by the magnitude of r prime. So we can say that the unit tangent vector is r prime over the magnitude of r prime. And the rate at which our position changes as we move along the curve is itself nothing but r prime. So if we divide this projection by r prime, we get the rate of change of the unit tangent vector, dt, with respect to t. And then divide that, don't have room to write it there, so magnitude of the projection divided by magnitude of r prime is equal to the magnitude of dt, where t is the unit tangent vector, with respect to t. Okay, the magnitude of, well, you understand, dt, d big T over d little t. Okay, and then the curvature, which is the magnitude of dt ds, is going to be the magnitude of d big T d little t divided by the magnitude of ds dt. Well, if we divide this, and that's just magnitude of dt dt times the magnitude of r prime, because magnitude of ds dt is the magnitude of our velocity vector, our r prime vector. This is speed, this is velocity. So to get from the projection to the time derivative of the unit tangent vector, we've got to divide by magnitude of r prime. Then to get from the derivative of our unit tangent vector with respect to time to the derivative with respect to position, we have to divide again by the unit tangent vector, and I wrote this as a multiplication. It's a rather intimidating division sign there. But this is what's going to happen. So we're going to have to divide this expression twice by r prime, and that leads us to the expression write it here, the curvature, kappa. And it's going to start looking grotesque because I didn't write it correctly the first time. But anyhow, our kappa, it looks more like a K than a kappa. There we go, that's not bad. Okay. Our kappa is our curvature, which is dt ds, and it's going to be this projection divided by r prime to get to our unit tangent vector, divided by r prime again to get from a time derivative to a position derivative. It's going to equal then magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. So we have a handy formula for calculating curvature, much easier to apply in almost any case than trying to do unit tangent vector, derivative of unit tangent vector, and so forth.